Hi everyone, welcome to my lecture series. In this lecture video, I'm going to talk about work and energy. So previously, let's see. So in this video, I'll talk about what work and energy are. So I'll give you those definitions. I'll be deriving what is called the work-energy theorem. And then I'll talk about different forms of energy. So this is actually something I would have done in class too, which is set up a little demo. So, good old internet, right? So I would set up a demo where I have a spring that's actually hanging with a mass. I brought my little mass here. I don't have a spring to work with. I mean, I guess I could find one, but, But anyway, so we have this mass and spring, and it's moving up and down, and I would ask you the question, which component of the spring has the most energy? Is it through the motion of the spring? Is it through the compression and expansion of that spring? Or is it at rest? So those are all of your questions. So I'd have you vote, and we take a vote and all that stuff. So of course, I'm going to go ahead and do that with you. I'm just taking a vote. Where do you think the energy is the greatest or maximum? During its motion, while it's at rest, or while it's stretching in the spring. So why don't you try that? Okay. So we'll also answer this question too. I love this photo because it's not me, but I have that jacket. I like to think, and I have a helmet that's white, and it's pretty amazing how accurate this photo is. So I'm going to pretend it's me because that person looks awesome, and they're like in the middle of, I don't know, Europe or something, or out west. It looks really great, right? But I'll talk about later in the video, which has more energy, a skier at the top of the mountain or the skier at the very bottom of the mountain. So what I did during this question, because this is what physics teachers do, right? Your phones have this thing called GPS or Runkeeper, or I don't know, there's all different sorts of apps in your phone that actually can track how far you've gone and how fast you go and your elevation. So that's what I did, because I used to, before my job here at Quinnipiac, I taught many years at high school, and I used to do the ski club there. And, so during ski club one day, I put my phone in my pocket and I turned Runkeeper on, and I got all my, stats about skiing. It was ski at Okemo. So I was really excited to see how fast it was going to go and how high and all that stuff. So I'll share that information with you. So what do you think has more energy? Same thing. I'm not going to quiz you in this one, but just think about it. It's an interesting question. So previously in physics, we've been studying and analyzing motion with Newton's laws, which requires us to draw some free body diagrams. If there's multiple objects, we need to do multiple diagrams. We need to consider x and y. It's not bad. It's not hard. It's hard. I'm not going to say it's not hard, but it's long, right? You got to know the directions. If you mess one direction up, the whole thing's wrong. All this fun stuff. So the good news is that when we use energy, we don't have to do that because we're going to use what are called scalar quantities. Vector quantities have a magnitude and direction, whereas scalars are just the magnitude. So instead of doing our analysis on the ramp, I'll show you later, of taking taking the rotated coordinate system and doing all that fun stuff. We're not going to do that. We're going to find out the energy at the top and at the bottom, and it's actually quite simple when you do it with energy. So it's a really great way to analyze motion, another approach at the system. So let's talk about work. Let me set up my stuff right here. So work is how effective is the force at moving an object. So this is tall enough. I'll bring it down a little bit. Okay. I don't need too much space here. Background's kind of dark, which makes me kind of hard to see. I just noticed that. I don't know why it's doing that actually, right? All my slides are like that. Oh. I've learned so much with technology in the past couple weeks. That's okay. So let me do a little demonstration for you. It's not super exciting, not going to lie, but it is going to prove my point though. So clearly this is not a book, but actually I like it because it's tall enough because you could see it in the video. So if I want to move this to this direction. I'll just say this direction because it's actually doing the opposite when I do it here. So it's the video is right, but my left. The most effective way to do that would be to push it that way. You don't need a physics degree for that. You know that if you want it to go to a certain location, you push it during that location. So it turns out that not all pushes are the same, because I could push this, but if I don't push it in the right direction, it's not really effective at moving this, right? So let me be really silly here. Say I want to move it to my hand, but I push straight down. Is that force effective? The answer is, of course, no, it's not. It doesn't move it to my hand. So work is kind of this idea, how effective your force is. Doing this is very effective. We say we have the maximum amount of work when this happens. When I do this, not very effective. This is no work because it never actually got to where I wanted to go. Now I can actually take this object and actually push it at an angle, right? And I can do this. It's effective, but not as effective if I just put all of my force horizontal as opposed to at an angle like this. So what happens is if I have an angle to my force, let's see if I can do this in a good view, there we go. If I have an angle to my force, then only the horizontal component really does the work in this case, because we want it to go horizontal. So we think about work in physics about how effective it is. We must consider the magnitude, so how much, you push this. Clearly, you push it a little bit versus if you push it like a lot of it. It's way more effective. Again, you don't need a physics degree for that. The direction, and actually how far it moves, right? If this thing moved a lot farther, then that force is really effective. So that's the conceptual idea of work in physics. Now, I'm going to just fast forward way down in my slides, but we talk about work because work actually tells us whether or not we have gained, lost, or maintained our energy. So work is related to energy. In fact, they're not necessarily interchangeable, but they're very closely related to each other. So work and energy are very, 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 very similar. So to quantify work, the way we do that is we define work, W, as force times distance times cosine of the angle. So here is an example, right? Say you want to take your block and move it to the right in this slide. Now, if you're pulling, this is an example of you pulling at an angle like this. So the most effective part of the work is going to be the work that's the force component that's parallel to your distance component. So notice that's the case here, right? This is the most effective way. And it's a projection of this horizontal force from this force, right? The vertical force doesn't actually move it in this direction, so it's not helpful. So the units for work is force times the distance, which is a Newton meter. And also another accepted and most widely used unit is called a joule. A joule is a unit of energy, and hence I talk about energy transfer here. The angle corresponds to the angle between the force and actually displacement. So technically, although this is in fact okay, it is relative to this line right here. And of course, the angle does change the quantity of work itself. When cosine is 0, if you remember all your fun trig identities, when cosine is 0, it gives you the value of 1, which means it gives you the full value of force and distance. So that's when you have your maximum work. And I'll write this down in a second because I have another slide about it. When cosine is 90, when you have up, it means you have no horizontal component. Essentially it means that the cosine of 90 is 0. So if the force and the distance are perpendicular, then this whole thing is not effective, and the whole thing goes to 0. Cosine of 90 is 0 times this makes it 0. And then in between, the angles in between are a fraction of this, because as we go from 0 to 90, the cosine becomes smaller and smaller and smaller, so you only get a smaller piece of it. And this, is, of course, is displacement, and F is for force for newtons. So let me just put this all up here. I don't like stuff like that. So when, like I said, I'm going to write this down kind of in a nicer little package for you. I like visuals, so let's do some visuals here. Oops. Try again. There we go. So typically the maximum amount of work, or positive work, happens, well, I'm going to be careful with this because positive work happens, how do I want to say this? Positive work is not just zero, but zero is basically the maximum work. That is true. When your displacement and your force are in the same direction, this gives you positive work. That's a better way to kind of think about this. So like pushing my water bottle like I did earlier in the same direction I wanted to go in. That's positive work. This means there's energy transferred to the system. In other words, the water bottle is gaining energy because of my push. That's a gain of energy. I have this later on, but why not? We have a gain. In fact, I'm going to color coordinate this thing because I like to do that. This is a gain of energy. Like that. So any value, so even, so you still get positive work even if you have an angle. So I just want you to be aware of that. But negative work happens when you have this case, when the force and displacement are opposite each other. Now, the orientation of the arrows themselves doesn't matter. So in other words, a negative work case could be an up force and a down displacement. This is also negative work as well, just because these things are in opposite directions. So the cosine of 180 gives you -1, so that's why this is what we call negative work. And this would be if you lay these two out next to each other. Well, I guess I'll do it the way I drew it. Notice that this does make a 180-degree system like that. So when this happens, when you have negative work, that's a loss of energy, or you lose energy when that happens. So the most, I don't know if I had another example. I'm pretty sure I did, but since it's up here, I'll just write it. Your biggest example is friction or drag. So anything that opposes your motion is, in fact, going to make your system less effective, right? So this would be this case. It would be me if I push this, and if you notice, once it leaves my hand, it has negative work because the object had slowed down. So the slowdown of the object kind of is a signature of negative work happening. Do I have that? Yeah, force friction on a box. So anything with friction are slowing down. And that's another couple keywords we could write here. So positive work, usually the object is gaining speed. And this is usually slowing down. And although one form of energy is based on motion, we can think of it this way, right? If you're gaining speed, you're gaining energy. And if you're losing speed, you're losing energy. Now, you can also have a case where you don't have any work. I explained one case is when the object doesn't move, right? So here's a case where the object's, we have a force on the object, but the object itself is not moving, so that would be no work. I like to think of, this case, being at home. I do a lot of home workouts, right? And you do a lot of static, there's some static positions that you do. Now, my body is actually doing work. You can't see it, but inside my body, the muscles are, firing and stretching and contracting, so there is work done. And even though I will sweat if I hold this up all day long, yes, I will. My arms are really sore. there is, no physical work here, even though I am kind of like working out as we define working out. And then the other case is when the force is perpendicular to displacement. So even though you're holding your suitcase up and you're moving this way, there's no work done on the system. So careful, right? So it's moving, yes, and there's a force on it, yes. But it's the fact that these are perpendicular. Cosine of 90 is 0, and that signifies no work. So this one is tricky, so just be careful with that one. All right, we have a bunch of different examples of work, so why don't we go ahead and start calculating some of these things. Mr. Cleans, let's see, a man cleaning the floor pulls the vacuum cleaner with a force of 50 newtons at an angle of 30 degrees with the horizontal. Calculate work done by the force on the vacuum as it displaces 30 meters to the right. So here we go. We have a force of 50 newtons at 30 degrees above the horizontal. Now, a good person modeling all the forces would have gravity on this too, and the normal force, which is good. It says nothing about friction, so we won't add friction. So I like to not only draw the forces, but where it's going. So the displacement is going to be 3 meters to the right. And notice I drew it as an arrow, because that's important as well. So work is going to be the force times distance times cosine of my angle. So essentially, this is, in fact, a plug and chug, which is nice. But let me just explain why. We're going to use this full force value. The distance is right here. Now, even though I didn't draw the distance right there, I could actually go all the way back. Let me do it that way. Got my force normal like this. I'll draw the displacement right here to show you that, in fact, that the angle between the force and displacement is 30 degrees. So we can go ahead and solve this out. 50 newtons times 3 meters times cosine 30 degrees, like that. 50 times 3 times cosine 30. So my answer is 129.9 joules, so that's pretty much close enough to 130 joules of work on this system. Now, if you notice, I totally ignored the normal and the force of gravity. But if you notice why I did that, I need a bright color. I do like the bright different color. We have blue, red, green. Okay. Fuchsia might be okay. Notice that the force normal is perpendicular to displacement and the force of gravity is perpendicular to displacement. They do not contribute any work to this problem. So the only thing that does is this 50 Newton force. And that's what I talk about right here. Okay, a girl pulls a wagon along a level path for a distance of 15 meters. The handle of the wagon makes an angle of 20 degrees with the horizontal. The girl exerts 35 Newton force on the handle. But now we have friction. Find the net work done on the force. So this is very similar to what we just done, except instead of just solving it out, we're going to find the work net by finding the force net times d. So if you see the net work, you need to use the net force. So we need to find the net force. So we have the 35 Newton force on a 20-degree angle, and we have friction of 24 newtons right here completely appropriate, but really not necessary in terms of solving it, is the force of normal and the force of gravity. So the net work done on the system. So you could do this a couple ways. I think the easiest way is to find the net force. And we can assume that, that the net force is going to be horizontal, and these cancel out anyway. So I'm just going to totally ignore the x direction for this. So what I have here is the following. This is my applied force, and this is my friction. So I like writing it symbolically. So my net force is going to be the component, right, Fa x of this, so Fax minus force friction. So that's going to be 35 newtons times cosine of the angle, which is 20, so I might as well just write it all in, times, let's see, subtract 24 newtons, there we go. 35 times cos 20 minus 24. My net force is 8.889, so I'm going to do 8.89 newtons of net force. Now let me just draw a quick picture of what I just found now. So I found the net force is horizontal of 8.89 newtons of force. So now that I want to find the work done, let me draw in the displacement. The displacement is 15 meters. Now it doesn't say we're going backwards, we assume we're going forward. So notice that my work net is going to be my force net times d times cosine the angle, which will be the following. My net force is 8.89 newtons. My displacement is 15 newtons. And my cosine, in this case, is 0. Now the reason why it's 0 is notice that these two are pointing in the same direction. If they're pointing in the same direction, then there's no angle between them. In fact, this will go to 1. So in other words, I'm just going to take 8.89 newtons and multiply it by 15 newtons. I get 133.35 newtons. It's a little different than what I did. But I think this is the most straightforward way. You can also do this other technique. Work net is going to be the work done by the applied force minus the work done by friction. You could also do that, where you calculate the work by both of those things. Now when you do that, the work applied would be force applied times d times cosine 30, right? Because that would be the work by that. And this would be force friction times d. So, just spot check this. I'm pretty sure this is okay. Cosine 20 minus 24 times 15. Yes, you get the same exact answer. So you could do it this way, where you do the cosine here instead of finding the net force. It's your personal preference when it comes down to which way you like or which one you think makes more sense. They're both acceptable ways to do it. One more. Okay. So a flight attendant pulls her bag. Work she does on the bag. Work done by friction, and then the coefficient of kinetic friction between that and the bag. Fun stuff, right? All right, so here we go. You know, so we have what? Gravity acting down. We have the applied force here, normal, and then friction on this object. So the work she does on the bag is by the applied force. So the work done, so part A is going to be work done by the applied force, which will be force applied times the displacement times cosine of the angle. So work applied is going to be she exerts 40 newtons. 40 newtons pulls at 253 meters times the distance, I did the distance, times the angle. Cosine of 52. I think I can squeeze it in before it gets lost. So 40 times 253 times cosine 52. Gonna just, yes, do that and do that. Very good. What do I get here? 6,230.5. I'm going to round that. And this is joules of energy. Then part B is, what is the work done by friction? Work done by friction is going to be the force of friction times D times cosine of the angle, right? Let's see if we have the force of friction. No, we do not have the force of friction. So then we go into our let's be clever mode, but this is what we would do. But as you can see, we don't have the force of friction. But we do have, this information, constant velocity, which means I can go back and shift gears and go back into Newton's second law analysis to find that information. So for my x direction, fx is going to be max. But since we're constant speed, this will be 0. So with that case, my net force is the following. Force applied in the x, right? Because my horizontal motion, when I analyze this, will be the green. So it's this and this part of my thing right there. Minus force friction is equal to 0. So in fact, my force friction is equal to the x component of the applied force. Okay, that's easy enough because I can't find that. I kind of found it already, but let's do it again. So 40 newtons times cosine of 52 is the x component of this force. And that's my force friction. So 40 times cosine 52. So my force friction is 24 newtons. I'm sorry, 24, there's some decimal places here, 0.63 newtons, just like that. Okay, so since I ran out of space up there, I'm going to continue down here. So for part B, my work done by friction is force friction times D times cosine the angle. Our force of friction is 24.63 newtons times 243 point, I'm sorry, 253, sorry, that's having a moment there, 253 meters, times cosine. So, as always, if the direction of distance is this way and the force of friction is that way, our angle is 180, which will yield a -1. So this is negative 6,230.5 joules. And yes, it is the same value but negative of that because it's moving at a constant velocity, which means the net work, because the net force is 0, the net work is 0. So fun fact. So if constant speed, then the work net has to be 0 because there's no net force. And I say this because if you were to add this one and the one above, her applied force right here and her force friction, they should cancel, which they do. Good news. See, what is a force of, what is the coefficient of friction? Okay. So, we know the coefficient of friction comes from the force normal times mu. Which means we got to find the force normal. So the force normal comes from the y component of our free body diagram, so we have to go ahead and think about that now. So we have the upward force, from the normal, the down from gravity, and we have the upward from the applied in the y. So, same thing, so the force in the y is equal to MAY, but there's no horizontal motion, so that's 0. Force normal is up, gravity is down, the force applied in the y is up. Up. Up means positive, equal to 0. So we can solve for this. If I move this over, this becomes negative, and if I move that over, it becomes positive. So force normal is going to equal to force gravity minus Fay. Now they gave us the weight, because it's in newtons, so this is force gravity already done for us. Woo. Force normal is going to be the 70 newtons minus the force applied, which was, how much? 40 newtons, right? It's been 40 newtons, yes, okay. 40 newtons times sine 52. So 40 newtons times sine 52 gives me 31. So 70 minus 31.52. I'll write it out, what I got, so you can see what I'm doing. Gives me, I'm sorry, that was the answer. I'll write the answer first, and then I'll put that back where it should be. And there you have it. So 38.48 newtons is our force normal. Now, that doesn't solve our question. Our question is, what is the coefficient of friction? So we calculated the friction force from earlier as 24.63. So now we can do this out. So 24.63 newtons is equal to 8.48 newtons times mu. Mu is going to be basically 24.63 newtons divided by 38.48 newtons. And then I get 0.64 as our coefficient of friction, so pretty good. And there you have it. So I know I advertised that we wouldn't do this, but trust me, it's after we get through work. After we work it out. Get it? Work out? We're working out? Get it? Sort of? I don't know. I have no idea how you took that. So I'm just going to pretend that you laughed. Anyway, moving on. Okay. Good news. We're almost done with work. So, work can actually be done by a varying force. Not that I emphasize that this was constant forces, but these are. But of course, reality is more complicated than that. So what happens is if you have work done by a varying force, if we plot the force over a distance, for example, like this, we can find the work by taking the area below the curve. So if this blue line is called the curve, we look at the area. Technically, we're doing an integral I won't, scare you by saying we're doing integrals, but we are doing integrals. But that's how we can find the work done by those kinds of systems. So now what this above and below means, so it's not showing you really good here, so I'm going to show you in this. So this dark line is the curve, okay? So just like we did with displacement and all of, reading graphs, is that the area underneath the curve right here is positive work. And then if we take the curve and go back to 0, that's negative work. So there's times when you can have no work done on the system. That happens. But that's how we can find the total work done. So here's a quick little example of doing the work on the system. So if I want to find the work of this graph, I would just basically find the area underneath this, right? So I would actually, let's see, there's a couple ways you could do this. There's a really fast way, but I'm going to show you the more probably practical way to do this. So just break it up into two parts, right? I could find the area of this little shape first and do the area of this shape. That's how I would do it. So the area of this shape would be, so part 1, it would be 3 times 6, which gives me 18 joules. Now it's above the 0 line, so these are positive. And this one's basically the same thing, but since it's a triangle, I have to apply the 1/2, the base, so from here to here is 3, times the height. It happens to be 6 as well. So basically 18 divided by 2 is 9. But the work is going to be part 1 plus part 2, which is going to be 18 joules plus 9 joules, which I'm going to do in a calculator because I don't trust myself. It was right, okay. Which becomes 27 joules of work done. Not bad. Things like this always look way more intimidating than they are. The other way I was thinking of is if you notice that this is basically a square of 9. So 9 plus 9, and this is 2 squares in half, so it's like another 9. So 9 times 3 is 27. That was my quick way of thinking about it, but I think, sometimes going more practical is good. So actually, one thing that does vary all the time because of its nature is a spring. So Hooke's law is basically showing you that a spring, an ideal spring, so yes, a perfect spring, will actually vary its force depending on its stretch. So I don't have... Okay, my elastic band is not Hooke's law, by the way, because it's not a linear displacement. But basically, the more I pull this, the stronger the elastic pulls back. That's what this equation's saying. It's saying that as I increase the distance I stretch it, the force that the elastic pulls back on is stronger. So K is the quality of this elastic, so how strong it is. If K is large, this is really hard to pull. If K is small, it's really easy to pull. So these are actually similar strength. I was actually pretty surprised that these actually are, I would say the Ks are the same of this. But like your car shocks would be an enormous K value. You need the whole weight of the car to actually push down your car shocks versus like a rubber band. But where was I going with this? Oh yes. So we're not going to technically calculate things just yet with this. Like I said, I keep saying wait because literally our second to last lesson is all about springs. But it's good to know that there is a real physical system that does vary its force as you change its displacement. So X is, yes, the stretching of the spring, so not when it's at rest, but when you actually stretch it out. The negative sign comes from the fact that if you pull the spring down, the spring is going to do the opposite and pull you back up. We typically ignore the negative sign when we talk about this just because we care about the values and not so much about the direction. But this is a directional feature right here. And like I said, we'll do more calculations with this. And more appropriately, what you get is you get graphs. What happens is you get a graph that looks like this. And this is a very, 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 very common physics lab. I don't know if we'll do it or not. But an ideal spring would be linear, and we'll do this. My hair elastic kind of gets weaker over time, so what happens is I get something more like this. So it kind of curves out. Now it's almost linear, but not perfect like that. But this is Hooke's law, that as the more you pull it, the more the force you get. But the force and the pull are proportional to each other. Is that crazy? I know lines are like probably the most boringest thing to look at, but if you think about what it means that this is a predictable thing. Crazy, right? Springs are predictable. Imagine, springs are usually crazy. I don't think them as predictable things. Okay, so what I'm going to do is quickly derive the work energy theorem for you. So let me do that. So before I do, I usually have this visual of a block being moved. And just like, I'm going to take a sip of this, but when I move this over here, it gains speed, right? It goes from not moving to moving. So that's kind of what we're having here. So, like I said, we have the block with some initial velocity. And because we pushed it, right, some distance d, we were able to, we pushed it, with some force F. So the force was over here, F. This is the same block, just over here. We were able to move it and actually change its velocity. So work is defined as force times displacement. I'm going to ignore the cosine part because we're going in the same direction. So it's the full value of the force, the work. So if you recall, force can be conveniently written as ma. So I'm going to replace that force with ma. And instead of having displacement here, I'm going to replace it with the change in velocity. So if you recall, we have this convenient kinematic equation. And usually I write it as delta x, but I'm going to write the variable d just to match here. It's the same concept. So I'm going to solve for d. So first I got to subtract the initial velocity away so that I have it like this. And then I'm going to divide by 2a on both sides so that I can get d. So I have a expression for d as vf minus vi equals 2a, like that. So I'm going to plug that into here. So it doesn't, sorry, I forgot the squares. It's not pretty. It's pretty ugly, actually. But watch what's going to happen. First of all, I can divide by the a's, and then I can go ahead and rewrite this. And another thing I'm going to do is I'm going to take this 2 and just stick it out here instead. So I'm just going to move the 2. Notice I put it underneath so it didn't change what this looks like. But now it's looking a little nicer. And now I'm going to distribute the 1/2 m right here, so I'm going to go ahead and do that. So 1/2 mv final squared minus 1/2 mv initial squared. So I'm going to define 1/2 mv squared as a form of energy called kinetic energy based on motion. So the work done, if you notice, is basically the kinetic energy final minus the kinetic energy initial. Or in other words, the work is equal to the change of kinetic energy. We call this the work energy theorem. Of course, I just abbreviated everything, but you get the idea. This is the work energy theorem. It says if there is work done on your object, it will change its motion. Hopefully that makes sense, because when I took this water bottle and I applied a force, it changed its motion. Now, if I have positive work, I gain motion or gain energy. If I have negative work, then I lose energy, so the change is negative. So it all works out. And if I have no work, then there's going to be no change of energy, which means the object maintains constant speed. Isn't that crazy? Everything works out. So, So let me just take another quick sip. So as I said, what we have here is we have the kinetic energy, and it's defined as energy associated with motion. So anytime there's motion in a problem, there is energy, at least kinetic energy. So kinetic energy is measured in joules because it is a form of work. So like I said, that energy-work relationship. And we measure the mass, of course, always in kilograms, and this is in meters per second, like that. So we can calculate the energy associated with an object just based on its speed. We'll do that a little later. But the work energy theorem can be written in so many ways. The original way is the net work on the system is equal to the change of kinetic energy. And I'll be quite honest, this is not a useful form. I find the bottom one to be the most useful form. Notice that I just made this into the change of kinetic energy. And then I took this and expanded it out to what it was. So if I know the force and the distance, of course, usually the angles, there's little to no angles that are involved, so it's either going to be negative or positive. So usually we drop that term. But we could figure out the change in velocity if we know how much we pushed it and how far. So like I said, this is really cool because now we're starting to get into the point where these are scalar quantities and we don't have to worry too much about the force. We're going to move away from forces. And the whole thing is, of course, measured in joules because we are using work and defining energy. So here's just a visual of this. I'm not going to go through this, but as you can see, we have a car. It's experiencing a force opposite the motion because it's actually moving here. And then the work is negative because we are slowing down in this case. And they go through it. So notice the 180 because of the force and the displacement. Now it's weird because they put the two arrows here. I think that's actually not helpful. If you look at the diagram, it started here and ended it here. So you have to think of it that way. Let's do some questions, and then I'll end the video at this point with the work energy theorem. So a forward force is applied to a loaded car over a distance of that. If the car is initially at rest and it has that final speed, what is the combined mass of its contents? So notice what we have here. So notice we have a force. We have a distance. We have a final speed, and we have the initial speed. So notice the most practical or the best form to use is FD is equal to mv final squared minus mv initial squared, because we have a force and a d. And like I said, most of the time it's not going to have an angle. It's usually unusual that it does. So that's why I just kind of dropped it out. If you really want the angle, it will be cosine of 0 because they're going in the same direction. So if you think about, I don't know what kind of cart this is, but the force and the displacement. So the angle is 0. So you'll notice that I drop it out. I hope that's comfortable with you. Okay, so 11 newtons times 15 meters is equal to 1/2. M is what we're solving for. And our final speed, so we have to be careful with this, but once the final speed first, this is something I know I always mix up just because, I'm moving too fast here. Now, good news, this is 0, but let's write it in to be good physics students and complete. So this whole term actually goes to 0. And this becomes way simpler to solve. So I'll go ahead and simplify the other side. So 11 times 15 gives me 165 equals, I'm going to simplify this side. So 1.98 squared divided by 2 gives me 1.96 m. Perfect. Gives me 84 0.18. Sorry, something